All right, hi everyone. So today what we're going to look at is with our stoichiometry, we're going to look at mole to mole conversion. So just a quick review of what stoichiometry is all about, right? It's about predicting how much reactant you need based on how much product you want, right? So we want to know, hey, if I want to end up with a certain amount of stuff, how much do I need to put in to end up with that final result? And it's very essential in chemistry. Now, here's an example: is airbags, right? So the amount of the nitrogen gas here, that's what fills up an airbag. That has to be an exact amount, because think about what would happen if the airbag did not inflate enough, or if it inflated too much, right? That would potentially seriously injure someone, right? So too much or too little would be bad news. So stoichiometry is very important because that helps us figure out how much of that reactant do we need in order to end up with the result that we're shooting for. Okay, and that's what stoichiometry is all about. Okay, so it's really how much reactant do I need to make a certain amount of product, right? It's how much waste product will you have to deal with. So if you you can calculate to figure out, all right, this is how much extra stuff I'm going to have if you want it or don't want it. And then it actually then for industry is going to be very useful because they're going to be able to figure out how much product you're going to be able to produce and then later sell. So now we're going to start by looking at just mole to mole conversion. So this is if you know a certain amount of moles and you want to know how many moles will you end up with. Okay, and we'll get into mole to gram stoich after this. All right, so first what we're going to do is look at coefficient review. So just kind of go over this. So here's a balanced equation, right, with the coefficients in front. We got to think about what does this mean. So the first thing is looking at, well, how many atoms of hydrogen do you have here? So there's your hydrogen, right, on your reactant side. You've got 3, but when you've got the coefficient in front, remember we're distributing that across. So how many hydrogens do you have? You should have said 12, right, because it's the 3 times the 4. Now what if we said how many molecules of ammonia are reacting in this equation? For this one, you should say 4, right? Because that's what this number in front is, right? It's talking about how many of these molecules we have. Now, what about this one? What about how many moles of ammonia are reacting? This one might be a little new to think about, but that's what these coefficients are also telling us, right? It's the amount of moles that they are. So remember, coefficients are nothing more than a ratio, right? They're showing this relationship between the products and the reactants. Okay, so that's what that's all about. So what we can do then is use stoichiometry and this balanced equation to then make predictions, right, as far as what we're going to end up with, and or if we know what we're going to end up with, we could figure out what we would start with. So look at this. If we have 4 moles of ammonia, they react and they produce how many moles of water? Okay, so if you have 4 moles of ammonia and they react with the oxygen here, how many moles of water are produced? Yeah, 6 would be this. Because look, if I've got 4, this, and it's just a ratio. So for every 4 molecules of ammonia, you're going to end up with 6 molecules of water. Now, this is where it gets a little bit more complicated. This is where proportions come into play, because sometimes, or often, you're not going to have the exact numbers that you have up here. Sometimes you're going to have numbers that are a little different. So look at this example. You've got 6.3 moles of ammonia, and we want to know how many moles of water are going to be produced. So this is where we're going to set up our proportion. Okay, so when you're setting up this proportion, remember we're doing the given over the goal, and then the conversion factor on this side, that's just the ratio. Instead of the mole sentence like we did last unit, now we're going to look at the equation up top here to get our numbers, our information. Okay, so let's go ahead and look through, and I'll see if I can draw and go through this with you. So the given in this problem is 6.3 moles of the NH3. Forgive my handwriting because I'm doing this with a mouse. Okay, and my goal then is, what are we trying to find? We're trying to find this, right? How many moles of H2O? So that's going to be my X, and then my moles of water, H2O. Okay, so that's my goal on this problem. All right, then on the right side, remember the right side, I'm going to go right up here to the equation and figure out, well, what do I need to put in? Remember, units have to match, so I'm going to have moles of the NH4 on the top, or I'm sorry, NH3, the moles of ammonia, and then on the bottom, it's going to be moles of H2O. Right, because that's what I had on this other side over here. So I just look up here and say, all right, where's moles of ammonia? Oh, look, right there, right? So I'm going to put the 4 up top, And then moles of water, where's that at? Right there. Okay, so then 6 goes down on the bottom there. Okay, once you get to this point here, all you have to do then is cross multiply, right? So I'm going to crisscross with my math, right? And then you end up with 4x is equal to 6 times 6.3, and your calculator gives you 37.8. Then to get x by itself, divide by 4 is 9.4, okay, as your answer. So this is a digital version of that, as you can see how it looks. And that's how you do it, okay? So pretty straightforward. So let's go through and we'll look at another example here. All right, now look at this one. So we have the problem is stating that we've got 0.35 moles of C7H16. How many moles of CO2 should we produce? Now, again, if this was you had 1, we would produce 7, right? But again, our given here is a different number. So what we do here is, again, set up our proportion. Okay, so let me get back to the pen here. And so our given in this problem is the 0.3, that's a 3, 0.35 moles of the C7H16. Okay, so that's the given. That's what we know from the problem. I'm just pulling that right from here. Okay. My goal in this problem, what are we trying to find? I'm trying to find how many moles of CO2, right? So that's going to be my X moles of CO2 down the bottom there. And we set that equal to, all right, now, again, units have to be the same. So I know that I'm going to have my moles of the C7H16 up top. And I know I'm going to have moles of CO2 down at the bottom here. Okay. So now, again, where do I look to get these numbers? Right up here, right? So for the C7H16, there it is, 1. Okay, so there's my 1 on top. And then on the bottom, CO2, 7, right? So I'm going to put 7 down on the bottom here. Okay, cross multiply this out, and you get 2.45 moles. Okay, so here's the kind of the more clean looking version of what we did. So there was our given, there's our goal, and there was the mole ratio, right? For every 1 mole of C7H16, you're producing 7 moles of CO2. And then remember in your answer to put units there as well. Okay, not too bad, right? All right, one more concept we want to touch on here, and that is percent yield. So what percent yield is, if you look at Calvin here, right? He said he got a C on his test, which he was happy with. But how do you figure that out, right? When you figure out a grade, what do? You take the grade you got on the test, right? Whatever score, and you divide it by what you could have gotten, right? The maximum possible score. So Calvin scored a 14. The test was worth 20 points. You divide that, you get 0.7, then you times 100, so 70%. Right? That's all percent yield is, right? It's kind of like we're grading our experiment. So what it is, it's what you put on top here is what you actually got. So when you conduct an experiment and you produce some products, right? You've got, this is how much we produced. And then what you do is you divide it by what you could have gotten. So the mathematical, right? You calculate it out. This is how much we should have gotten. So all you're doing is taking your experimental value, what you actually got, and then you divide it by the theoretical value, what you should have gotten, and then you get a percent, right? So it's just the ratio of actual yield to the theoretical yield, and then we just divide it, multiply by 100. So if your actual yield is equal to your theoretical yield, that means your percent yield is 100%, right? And that would be the ideal, right? If you want to try to get exactly the correct amount, right? We want those to be the same. So percent yield, if you're at 100%, that means thumbs up, right? You're getting exactly what you should have gotten. Usually, though, the percent's lower than 100% because the actual yield is often less than the theoretical. So usually you don't produce quite as much as you theoretically should have. And the reason for this is because a lot of times reactions don't occur all the way. Sometimes there's some loss, experimental error could be in there as well. It's possible to end up with over 100%, right? You could end up with more, and that just means that more sample was recovered than predicted, right? And that also could be maybe you didn't measure stuff correctly. So there's a few different reasons for that. But that percent yield is an absolute value. It's always going to be positive. Okay. So how do we solve these problems? So we just figured out on that last problem, if you remember, that if we reacted to 0.35 moles, that we should produce, so theoretically, mathematically, we should have produced 2.45 moles of CO2. Well, let's say you do that experiment, but you actually collected 2.35. So you didn't quite get the 2.45. The question then is, well, what is your percent yield? Okay, so for this, all we have to do is take our what you experimentally got. So we're going to take the 2.35. That's what we actually got, right? Moles. And then theoretically, though, we should have gotten 2.45, right? Calculate that out, and then you're going to multiply that by 100. Now, when we do that, you end up with this here. So 2.35 divided by 2.45 is 0.959, and then you times that by 100, and you get 95.9, which we can round to 96. So 96% would be the percent yield, which is actually pretty good, pretty close to 100. Okay? All right, that's it, you guys. If you have any questions, make sure you ask questions in class. See y'all later.